In this video, we're going to review all the types of surfaces we've studied so far in our course, and then we are going to look at some equations and try to figure out what they look like, figure out what their graphs look like. So here's our first surface. The first surface we studied was a plane, or actually I think a sphere was the first surface we studied, but plane is one of the first surfaces we studied. It's given by a constant times x plus a constant times y plus a constant times z equals a constant, or some rearrangement of that. If you have the plane written in this form, the normal vector to the plane is ABC, and that number d on the right hand side distinguishes all of the other planes that are parallel to it from the particular plane that you're interested in. When we're trying to sketch these, we usually can't sketch the whole thing. Usually the best we can do is draw the little triangular slice that we see in the first octant. So this is what we'll see again and again as we're sketching planes. Now, when we learn the distance formula, we use the distance formula in 3D to derive the formula for a sphere. If the sphere has center x naught, y naught, z naught, the equation is given by this. We've got x minus x naught squared plus y minus y naught squared plus z minus z naught squared. There's nothing in the denominator, equals r squared. If you take the square root of the right hand side, that's the radius of your sphere, and x naught, y naught, z naught is the center. Now this is just a particular example of a cylinder, but a cylinder in this class consists of a generating curve and all of the lines that go through the generating curve that are parallel to a line that's not in a parallel plane. That's a lot of words, but basically what it is, in our class we're going to look at right cylinders, and the equations will have two variables or maybe one variable. And the cylinder's rulings, those lines that comprise the cylinder, are going to be parallel to the axis whose variable is missing. So on this one I've got z equals y squared. The rulings in this case are parallel to the x-axis. So what we really see is a parabola, but x is free to be anything. So that parabola is sort of coming out of the page and coming toward us. And we're drawing it from this perspective so that we can kind of see what's going on. But z equals y squared, kind of, it looks like this. It's hard to draw, or hard to do with my camera. So it looks like this. That's z equals y squared. It's a parabola, and it's coming out at us. Okay. Now the next four quadric surfaces that we studied all had very similar forms. Let's talk about the differences between these equations and how you can tell the difference between these four. Now notice all of them have x squared, y squared, and z squared in them. If the x squared, y squared, and z squared terms are all positive, and there's a 1 on the right hand side, or you can make it a 1 on the right hand side through algebraic manipulation, then if you let one of these terms go to 0, so you let z equals z naught, the cross section is an ellipse. And if you do that for all of the terms one at a time, you let this one be 0, and then this one be 0, and then this one be 0, you see all the cross sections in the planes parallel to the xy plane, the yz plane, and the xz plane are all ellipses. So we get the 3D analog of the ellipse. It's the ellipsoid. Notice that all of them are positive, and we've got a 1 over here. Now, the hyperboloid of one sheet looks very similar, at least this equation does, but the graph looks very different. X, y, and z are all squared. You've got a 1 on the right-hand side, or if it's not a 1, you can make it a 1. If that was a 10, I could divide everything by 10, and it would be a 1. And notice I've got two terms that are positive and one term that is negative. This results in a hyperboloid of one sheet. Notice that the negative is in front of the z term, and our hyperboloid of one sheet is parallel. It's opening parallel to the z-axis, or it's opening around the z-axis if that center is on the z-axis somewhere. The center has a z-coordinate of 0. So that's what a hyperboloid of one sheet looks like. Two positives, a negative, a 1 on the right-hand side, and all three variables are squared. Now, if we have almost exactly the same thing, but instead of having two positives and a negative, you've got two negatives and a positive, we end up with this hyperboloid of 2 sheets. Now this is a little different. The positive term indicates that axis of symmetry. So the positive term is on the z this time. The x and y are both negative. So the hyperboloid has 2 sheets or 2 pieces, and those pieces open around the z-axis. Or if the center is something other than 0, 0, 0, it's going to open along a line parallel to the z-axis. Notice that the right-hand side is 1. So for all of these, we've got a constant on the right-hand side. If it wasn't 1, we could make it 1 by dividing. All 3 variables are squared here and here and here. They all have 1s. The ellipsoid has all 3 positive. The hyperboloid of 1 sheet has 2 positive and a negative. The negative indicates the axis of symmetry. Hyperboloid of 2 sheets has 2 negatives and a positive, and the positive term indicates the axis of symmetry. Since the positive is on the z term, it opens in the z direction. Over here, since the negative is on the z term, it's the one that doesn't match the other ones, it opens in the z direction. Now we could change that negative. The y could be negative instead of the z, and then it would open in the y direction instead. Or the x could be negative instead of the z, and it would open in the x direction. Now the cone looks very similar to the hyperboloid of 1 sheet. You've got 2 positives and a negative. But notice the right-hand side is 0. This is critical. We have no constant over here. We're not just going to subtract constant from both sides after you've completed the squares, and that'll be necessary sometimes. If the right-hand side is 0, and you've got 2 terms that are all 3 variables are squared, 2 are positive and 1's negative, or 2 negative and 1 positive, we could multiply everything by -1, we get an elliptic cone. So those are, I would think, a family of quadric surfaces where we've got all of our variables squared, and then depending on the number of negatives in our equation, we either get a hyperboloid of 1 sheet or 2 sheets, or an ellipsoid if there are no negatives, or if there's a negative and a right-hand side of 0, we get a cone. Okay, then the last type of quadric surfaces that we looked at were these types of quadric surfaces. Here we've got 1 variable raised to the 1st power. And in these pictures, z is raised to the 1st power, but we could switch. We could let x be raised to the 1st power or y be raised to the 1st power. But if z is raised to the 1st power, and the x and y are both squared and they both are positive, it looks like this. Now, if they are both squared and they're both negative, well, that's just this flipped upside down because of transformations. So if they have the same sign, you've got 2 variables squared, and then you've got another variable raised to the 1st power, then we're going to see something that looks like this. Now, if you've got 2 variables squared, and one of them's one term is positive and the other one is negative, and then the 3rd variable is raised to the 1st power, we get this thing. It looks kind of like a Pringle, a saddle, something like that. It's concave up in one direction and concave down in another direction. So with this one, the x term is positive, so it's concave up in the x direction. And the y term is negative, so it's concave down in the y direction. So concave up here, concave down here, and we get this saddle. Or you could switch it. So the y is positive and the x is negative, then it's going to be concave up in the y direction and concave down in the x direction. I'm never going to ask you to draw these, but I may ask you to match these with a given equation. Okay, so now we've talked about all of those. Let's look at a list of equations and try to identify them by type and sketch them. Okay, so let's look at the first one. Notice all 3 variables are squared. We've got a 1 on the right-hand side, and all 3 variables are positive. We're also not subtracting anything from the x, the y, or the z. So the center is 0, 0, 0, because we're not subtracting anything from the x, the y, or the z. And since all 3 variables are squared, all of these guys are positive and there's a 1 on the right hand side, we have an ellipsoid. To figure out how long this ellipsoid is in the x direction, the y direction, and the z direction, we look at these numbers in the denominator. Now, since there's a 4, which is a 2 squared under the x, we're going to go plus and minus 2 units in the x direction. So you're going to go to negative 2 and positive 2. Those are on our ellipsoid. And then since there is a 3 squared under the y, we're going to go plus and minus 3 units in the y direction. So we end up with this ellipse in the xy plane. And then since there is a 5 squared under the z, we're going to go plus and minus 5 units in the z direction. And that's our ellipsoid. Okay, now this one, you might be tempted to tell me that it's an ellipse, but it's not an ellipse. That's what it looks like in 2D. In the xz plane, it's an ellipse. There's an implied 1 squared there. So that is the equation of an ellipse. Now I've got a 100 on this side, so if I want that to be a 1, I might divide both sides by 100. So I've got x squared over 100, which is 10 squared, plus z squared over 900, which is 30 squared, and that equals 1. You'd say, ooh, oh my goodness, what does that look like? Well, you're going to go plus and minus 10 units in the x direction and plus and minus 30 units in the z direction. So I'm just going to go 1, 2, 3, that's 30. Every tick mark represents 10, so that's 10 and that's negative 10. We're going to see this ellipse in the xz plane back here. But what do you notice? Do you notice that there's no y here? Since there's no y is free to be anything. So this is a cylinder. It's not a traditional cylinder, it's a non-traditional cylinder. Cross sections are ellipses, they look like this, but since y is free to be anything, we're going to keep seeing that ellipse for y equals 0, y equals 10, y equals negative 10, and so on, and it's going to go all the way to the far left, and it's going to go all the way to the far right, and I can't draw the whole thing. But this is an example of a cylinder. Alright, now this one looks a little bit like an ellipsoid. Got an x squared, a y squared, and a z squared. But notice I've got 2 that are positive and 1 that's negative. So with 2 positive and 1 negative, it could be a hyperboloid of 1 sheet. But notice there's a 0 on the right-hand side. So what does that tell us? If you don't remember, get out your sheet and say, ah yes, the elliptic cone has 2 positives, a negative, a 0, and all 3 variables squared. Now with our cone, the axis of symmetry is parallel to the axis that corresponds to the negative term, the variable in that negative term. So this variable is z, it's in the negative term, so this one's parallel to the z-axis. Look here. Well, the y is negative, so it's going to be parallel to the y-axis, so it's going to open left and right. And the center isn't 0, 0, 0 this time. So let's identify the center. I look at the x, the y, and the z, and I see what I'm subtracting from the x, y, and z. So whatever sign I see there, I'm going to take the opposite sign. So x naught, y naught, z naught is 2, negative 3, and 4, because I'm taking the opposite sign of those 3. So we're going to go to x equals 2, y equals negative 3, and z equals 4. Draw a rectangular box. We just do the best we can. It doesn't have to be perfect. So we go 2, -3, 4. And we're going to have a cone that opens in the y direction. So I'll just draw it like this. It doesn't have to be perfect. I always say that over and over again. Yeah, we're not worried too much about that 4 and that 9 and how it would change the cone. If you want to make a better picture, you could take those into account. I just want to make sure that it's parallel to the y-axis the way it's supposed to be, and that it has the right center. And the center is 2, -3, 4. If you're graphing these on a test or a quiz, just labeling the center is fine. And you might just say y direction symmetry if you don't think that it's clear from your picture. Okay, what about this one? X and y are positive, z is negative. I've got a 1, so this is a hyperboloid of one sheet. Notice the x, the y, and the z are all squared. So a hyperboloid of one sheet, and because the z term is negative, it's going to open parallel to the z-axis. So let's identify our center. Our center is x naught, y naught, z naught. It's the same as the last one. It's 2, -3, 4. So we go to x equals 2, y equals -3, z equals 4. Plot that point. That's the center. But what's the shape? It's a hyperboloid of one sheet. Forgot to label this one. This was an elliptic cone. This is a hyperboloid of one sheet. It opens parallel to the z-axis. So it's going to look like that, roughly. Okay. What about this guy? This one, it's very tempting to get the wrong answer on this. But notice, this time all of our variables aren't squared. We've got a y to the first power. Whenever you have a variable to the first power, you want to get that variable by itself. So I would solve for y by subtracting x squared and z squared from both sides. And that's nothing. That was something I was trying to get rid of earlier. So I'm subtracting the quantity x squared plus z squared. Notice x squared and z squared have the same sign and they're both negative. Since they have the same sign, this is an elliptic paraboloid. Now, if this 3 wasn't here and that minus wasn't there, this would be an elliptic paraboloid with its vertex at the origin, and it would open around the positive y-axis. But we multiply by -1, and that flips it, so it opens around the negative y-axis, and then we add 3 to all the y values, so it's going to shift it 3 units to the right. So it's an elliptic paraboloid facing the negative y-axis. When x and z are 0, y is 3. So there's the vertex. So we see something that looks like that. Okay. All right. Now if somebody asks you for the center, it's really more of a vertex in this case. We're not subtracting anything from the x or the z, so we have 0, 0 for x and z, and then to figure out what y would be, just plug that in for plug in x and z, and you get y equals 3. So there's our vertex. Okay, now this one, I hope you recognize it. You've got x, y, and z squared. You've got a constant on this side. There's nothing in the denominators this time, but an implied 1. So this is a sphere. Since if all the variables, or excuse me, if all the numbers that are in the denominators are the same, and you can multiply both sides by that and get it over here, then it's a sphere. So like think of our ellipsoid. We go plus and minus 2 units in the x direction, 2 units in the y direction, or 3 units in the y direction, and plus and minus 5 units in the z direction, so we get this. But if these were all 25, we'd go plus and minus 5 units in the x, plus and minus 5 units in the y, plus or minus 5 in the z. So that ellipsoid would be a very special ellipsoid. We'd call it a sphere. It'd be better to just multiply both sides by 25. Now this time, we don't have to do that. It's already in the standard form of a sphere. So the center is easy to just read off of the equation. We're not subtracting anything from the x or the y. So x naught, y naught is 0, 0. And we are subtracting a 1 from the z. So take the opposite sign. The center is 0, 0, 1. Radius squared is 1. So the radius is 1. So I want to plot a point at x equals 0, y equals 0, z equals 1. So we're right there. And the radius is 1. So we want to go up 1 and down 1, left 1, right 1, forward 1 and backward 1. And that's our sphere. What about this guy? X, y, and z are all raised to the first. And I get a constant on this side, so this is a plane. And what is its normal vector? I hope you said 2, 3, 4, because it is. We just read off the coefficients. Now I can't sketch the whole plane, but I can sketch the part of the plane in the first octant. So we'll let 2 variables be 0, solve for the third. Let y and z be 0. We get 2x equals 12, so x equals 6. Let x and z equal 0. We get 3y equals 12, so y equals 4. And x and z, or x and y equal 0, z equals, or 4z equals 12, so z equals 3. So that's our plane. That's the part that we see in the first octant. And the normal vector, which would be pointing out at us, has these components. We go 2 units in the x direction, 3 in the y, and 4 units in the z direction. What about this one? What type of surface is this? Notice we've got a z to the first. Okay, so that tells us something. It's either, if the z is raised to the first power, an elliptic paraboloid or a hyperbolic paraboloid. It's like a saddle point. Notice the x and the y are both squared, but this one is negative and that one's positive. So this is the saddle. And that plus 6 is just going to shift the whole graph up 6 units. So let's find the center. When the variable is raised to the first, it's a little bit harder to figure out the center, because you can't just look in the parentheses and see. But it's actually not too bad if you think about it. For x naught and y naught, we're just going to take the opposite sign of what's there. So I see a plus 3, that's going to be a minus 3. I see a minus 4, that's going to be a plus 4. Now I imagine plugging these x and y values in here. So that's 0 and that's 0. When those are 0, I solve for z and I get z equals 6. So that's the center point. So we're going backwards 3 units in the x direction, 4 units in the y direction, and up 6. And I'm drawing my rectangular box so I can get some sense of where that center is. Back 3 to the right 4 and up 6, so we're here. Oops, I'm sorry, it's off the camera screen. Alright, so we go back 3 to the right 4 and up 6, and we're here. And now this is concave up in the y direction, concave down in the x direction. So I'm just going to try to draw something that's concave up in the y direction and concave down in the x direction. You see my saddles all look the same. This is the best I can do for a saddle. It's the best way I could think about it. So it's opening like that, parallel to the y-axis. All right, last one. I've got x squared. I've got an x squared term, a y squared term, and a z squared term. I've got a 4 over here, which I could easily make a 1 by dividing both sides by 4. So it's either a hyperboloid of 1 sheet or 2 sheets, because I've got negatives and a 1. Now since I have 2 negatives and a positive, this is a hyperboloid of 2 sheets. X naught, y naught, z naught is given by what we're subtracting from the x, the y, and the z. Take the opposite sign, so that's a 3, a 4, and a 2. Okay. Now our hyperboloid of 2 sheets opens. It has an axis of symmetry, and that axis of symmetry is parallel to the axis of the variable whose term is positive. I know that's a mouthful, but I look at this one. This one's positive. It's got an x in it. So our hyperboloid of 2 sheets opens parallel to the x-axis. It's a little bit hard to draw, but we'll do the best we can. So we're going to go to x equals 3, y equals 4, z equals 2, draw a rectangular box, right there, and it opens parallel to the x-axis. So I'm just going to keep extending that in both directions. There's a line right there, just keeps going. Our sheets open around that line. Hard to draw, but I hope you get it. It's on the, did I do that right? Yeah, it's on this line right here, which is parallel to the x-axis over here. All right, guys. So that's how you do that. If I give you an equation, I might ask you to find the center and then identify the type of surface, and it's definitely going to be one of these types of surfaces. Remember, if one of the variables is missing, it's a cylinder of some kind. Cylinders don't look like cylinders anymore. They just look like some curve where a third variable is free to be anything. Planes look like this, spheres look like this. Here all the variables are raised to the first. Here all the variables are squared. You've got 1's in the denominator and an r squared on the other side. Then for these 4 guys, all 3 variables are squared. If there's a 1 on the right hand side, it's a hyperboloid of 1 sheet, 2 sheets, or an ellipse. If all 3 are positive, it's an ellipsoid. I said ellipse, but I meant ellipsoid. If all 3 are positive, it's an ellipsoid. If 2 are positive and 1's negative, it's a hyperboloid of 1 sheet. If 2 are negative and 1 is positive, it's a hyperboloid of 2 sheets. If it looks just like that, but instead of having a 1 on the side, it has a 0, it's a cone. And then if you've got a variable raised to the first power, it's either an elliptic paraboloid, facing up or down or left or right or front or backward, depending on what variable is over here, or what's called a hyperbolic paraboloid. Excuse me. And those look like this. In the next video, we will look at completing the square to get a surface whose center is not 0, 0, 0 in standard form, and then identifying it and graphing it.